Students. Welcome to the 17th day of 45 days JEE crash course. So, we have started the electrochemistry part. Okay, so in the last class, we have covered the conduction part. Now, we will today move to the next part of this chapter. Disclaimer: the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the images. So, what are the topics that I am going to cover today? So, first of all, we will see the electrode and half cell. So, we will look upon basically the construction of that electrolytic cell, galvanic cell, which we have studied up in the previous class. Then we will see the salt bridge is again a component of the same galvanic cell. Moving on further, we will try to compare the electrolytic cell and the electrochemical cell. Then representation of cell, and then we will move to the I would say quantitative part of this galvanic cell, which is EMF and all, and electrode potential and standard electrode potential, electrochemical series, and at last, I would say the most important thing is in the last, which is our Nernst equation and its application. Starting from electrode and half cell. So, what is first of all, look at the structure. So, whenever you have a metal M, right? You have a metal M. Okay, you have a strip of metal M. You dip it into the solution, and that metal M is called electrode. That strip of metal is called electrode. And now you dip it in the solution, and that solution contain the Mn positive, which is an ion of the same metal. And this combination of the metal electrode and the solution is called a half cell. Okay, basically you take a container, you take the solution which is having a metal salt, and the metal salt metal is taken as the electrode, right? So now if you just dip this do this setup, then three kind of interactions are possible. The first interaction would be that their Mn plus may collide with the electrode and undergo no change, means there is no change observed. Second thing that you will observe, means you can observe, is that Mn plus will collide with the electrode and gain an electron and can be converted into M. Basically, you are going from here to here. Means your Mn plus is getting electron. In that case, your ion is reduced. And this is represented with this equation. So this is the reduction of Mn positive to M. The third interaction which you would expect is that your metal is from the electrode is losing electrons, and it is losing an electron and moving on to Mn positive. Now in this case, since it is losing electron, so the metal atom is oxidized. So this can be again represented with the help of an equation, which is an oxidation equation of the same metal is. So these three types of interaction are possible whenever you dip a strip of metal, that is your electrode, into the electrolytic solution. So if I try to brief all of this, so about oxidation, reduction and all of this. So first of all, if you talk about the anode in case of electrolytic cell, then it will have positive sign and the cathode will have negative sign. Whereas in voltaic cell, your anode will have negative sign and cathode will have the positive sign. Talking about the electron flow move from anode to cathode, and in case of voltaic cell, it will also move from anode to cathode. What about half reaction? So in electrolytic cell, here the oxidation will occur and here the reduction will take place. Same as here also, in the galvanic cell, oxidation will occur on the anode and reduction will occur on the cathode. So the only difference is about the sign. Okay. Now moving on to the next part. So there are different type of half electrodes that are possible. Okay, so first one is the normal hydrogen electrode. So in the normal hydrogen electrode, what do? Is we take basically a hydrogen gas, and for that hydrogen gas we take platinum as the metal strip. Okay, because hydrogen in the solid form is not possible. Next is the important one, which is called as standard hydrogen electrode. So this is called as standard hydrogen electrode because we are taking the gas, that is our hydrogen, at 1 atm pressure, and the concentration of H plus in the solution is also taken as 1 molar. Okay, so basically your H plus is going to H2. Now what are we doing is we are taking the concentration of this H plus as 1 m, that is 1 molar concentration, and we are keeping the pressure of hydrogen as 1 atm. Last one is the calomel electrode, which is basically also a reference electrode. So it is a mercurous chloride electrode. Okay. So for that, what is the reaction? So we have Hg, we are reacting with Cl minus. So we get half Hg2Cl2 and release of one electron. So these are the three types of electrode, means they are special type of electrode which you will encounter to and fro. Next, let us talk about the salt bridge. So basically, what is salt bridge? This is basically a U-shaped tube and a gel permeated with a solution of inert electrolytes such as NH4NO3. And the ions of the inert electrode do not react, and the other ion in the solution, they are not oxidized or reduced. The salt bridge is necessary to complete the electrical circuit to maintain the electrical neutrality. So it is basically important to maintain the electron neutrality, because as soon as you start the reaction, there is a accumulation of positive and negative charge. So to just nullify that thing, what do? We put this U tube type of thing, which is called as salt bridge, and inside that we have the electrolytes that do not take part in the reaction. They just neutralize the extra charge in both the compartment by the flow of ions. So this is the overall picture of this say galvanic cell. So here is a salt bridge, right? So this is a salt bridge. Now as soon as this reaction start, you can see that this solution is containing zinc. So zinc 2 plus will go to zinc, right? So what will happen as a result of this? So zinc 2 plus must have a counter anion. Okay, so this counter anion is being accumulated in this solution. Okay, now similarly, when you are introducing your, suppose your, now the electron goes from here, moves on to here and comes here. Now when this electron comes here, the copper plus solution that we have, it has Cu2 plus. So that Cu2 plus take electron from this metal surface, and now what you have, what you would see, that your Cu is releasing your electron. So again I am saying it. So this is basically your electron flow. So here your zinc is going where? The zinc is going to Zn2 plus, and electrons are being liberated here and they move here. Okay, as they move here, the copper 2 plus take this electron and they go to the metal strip. So here what will happen? Since oxidation is occurring, so your Zn is going to Zn2 plus. So the number of cation has increased here, and here the number of anion has increased. To neutralize both of this, the salt which contain salt, which will in which the negative part will move in this side, and the positive part will move on this side, and they will just neutralize the extra cation of this side and extra anion of this side. Clear? Okay. So this is about the whole functioning of this cell. So this can be represented with the help of equation which is given here. So Zn is going to Zn2 plus and Cu2 plus is going to Cu. Difference between electrolytic and electrochemical cell. So I am telling it quickly. So what are the difference? The device in which electrolysis means chemical reaction involving oxidation is carried out by using electricity. Means electricity is used to carry out this redox reaction. Whereas in case of your galvanic cell, the electricity is used to carry out the chemical reaction. Okay, so the device in which electrolysis means the chemical reaction is carried out using the electricity, and in this case electricity is being produced using the chemical reaction. So both are opposite of each other. Okay, so this is our cell, right? So this is our cell. So this is the first one, which is the electrolytic cell, and this is the second one, which is the voltaic or galvanic cell. So again I am repeating it. So in the electrolytic cell, your external current is applied to do the chemical reaction, and in case of galvanic cell, the chemical reaction is aiding to perform the or produce the electricity. You can see that the battery is being blown here, and here the electricity is being provided with the help of the battery or cell. Now in electrolytic cell, anode is positive electrode while cathode is negative electrode. We have seen it. Now where in the case of galvanic cell, anode is negative electrode and cathode is the positive electrode. Okay, but in both of them, anode is the site of oxidation and cathode is the site of reduction. So this is same for each of them. Next, in electrolytic cell, ion are discharged at both the electrodes, while in galvanic cell, ion are discharged only at cathodes. Okay, so this is an important point. You should remember this. So if you consider the electrolytic cell, then ions are discharged at both the electrodes. Okay, ions are discharged at both the electrodes. So where in galvanic cell you know it very well that oxidation is occurring here. So here only your ions are discharged. Here no ions are discharged, right? But in this case, on both sides ions are discharged. The last one, in the electrolytic cell, both the electrodes are fitted in the same compartment. You can see it very clearly that there is no separation between them. But in the case of the voltaic cell, you can see a separation or partition. And in some cases, you will also notice that two different compartments are even used to carry out this voltaic or galvanic cell reaction. Now talking about a very important thing which is important for your numerical questions. So what is that? So it is representation of a cell. So let us consider a Daniell cell here. So this is the Daniell cell representation. So here you have zinc which is going to Zn2 plus, and here you have copper 2 plus which is going to copper. Now this is your half cell reaction that is occurring at the anode on the left hand side, and this is a half cell reaction which is occurring on the cathode on the right hand side. And the left hand side we have the single line. This single line denotes the phase boundary, because this zinc is in solid state whereas this zinc 2 plus is in the aqueous state. Similarly here also, to represent the phase boundary we have the copper solid and the copper 2 plus, and in between we have this single line. Now this double line is why is there? It is there, so it is representing the salt bridge. So the salt bridge is represented in this way. So you can see how clearly and how beautifully this representation represents the whole reaction without any much detailing or without any much writing. If I talk about the electron flow, so since electron are being released in this oxidation part and it goes and is consumed for the reduction part, so electron is flowing from left to right. So this is our cell reaction. Again, same things are mentioned, you can just go through it. So in reaction, the at anode the oxidation take place, so Zn goes to Zn2 plus, whereas in cathode the reduction take place, Cu2 plus go to Cu. If you talk about the terminal, the anode is negative, cathode is positive, and the side of the oxidation is the left hand side. So it is just a convention, you can think of it. So yeah, it is in the real time it is not making any sense, but to keep things simpler, we use a convention that we will do oxidation on the left hand side and the reduction on the right hand side. And this is the individual representation of each half cell. Zn is going to Zn2 plus and Cu2 plus is going to Cu. Next is EMF of a galvanic cell. So why do we see a EMF? So the in electrochemical cell, the electrodes in different half cell have different reduction potential. Means each have a different tendency to get reduced. Now the difference in the electrode potential of electrodes due to which the electron flow from anode to cathode is called electromotive cell. So basically when you dip your metal strip into the solution, there is a potential developed between these two. Similarly, on the RHS side also a same potential, means potential is also developed on the RHS side. Now two potentials are developed on the either side and you have connected it with the help of a wire. So if you are connecting two different potential with the help of a wire, that creates a potential difference, and that results in the flow of electron, which is the EMF of the cell. Now this is the driving force for each cell reaction that you see. Now if we connect two different electron will flow from electrode of higher negative electric charge density to the electrode with a lower electric charge density. A property closely related to density of negative charge is called the electrode potential. The potential difference between the two different metal and metal ion in which the electrode is dipped is called electrode potential, known as E. Okay, same thing is mentioned here, that whenever you dip these things, there is a charge density that is being accumulated, and that charge density is closely related to this electrode potential. Okay. Now if I talk about the standard state, when the pressure is 1 atm and temperature is 298 Kelvin and concentration is 1 molar, then the electrode potential of that cell is represented with the help of E naught. Okay, you must have seen this multiple times, E naught. So this is basically the standard condition, means the electrode potential of the given metal at standard condition. So according to your international convention, if the standard electrode potential of a half cell is 0.34, it means that it has a standard reduction potential of the half cell for this reaction. Okay, so basically what it is given, so suppose it is written that E naught Mn plus Mn. What does it mean? It means that your metal is going from Mn plus to M, and this value that is associated with this whole representation is the standard reduction potential. So this not stand for the standard condition, and since we are gaining electrons on going from left to right, means from Mn plus to M, that means reduction is occurring, and it is given by this equation. So whenever you see in this direction, that is from left to right, Mn plus to Mn. Same you do in the cell representation. Now if E naught oxidation is equals to X volt and E naught reduction is equals to minus X volt. So this is very important means conclusion for you. So if you have the reduction potential or the oxidation potential, you can know the opposite of them respectively by taking the negative sign against the value that you know. Okay, suppose your reduction potential is 2 volt, then your oxidation potential will be minus 2 volt. And if your oxidation potential is minus 3 volt, then your reduction potential will be plus 3 volt. So as simple as that. Now E naught cell or E cell is the potential difference between the two electrodes. So now what we are taking the whole cell. So initially we were talking about the electrode potential of the half cell. Now, if you take the difference between those two, then it is called the E naught cell or the E cell. If it is standard condition, then E naught. If not standard condition, then E cell. So this thing is called the standard EMF of the cell or the EMF of the cell. Clear? Or the cell potential or the cell voltage. So suppose you know the oxidation of one of this and reduction of the other. Okay, this is one case. Or if you know the E oxidation, which is not the standard condition, and you know the E redox, then in both cases you can calculate the EMF of the cell. But you should remember this, that this E naught X is for the species which is going oxidation, and this E naught reduction is for the species going under reduction. So that thing is being written here. So in case you don't know the E naught reduction of the given species, but your E naught oxidation is given, you can just take the negative sign and do it by the given formula. So this formula is applicable for everywhere. Okay, and but you should know the oxidation potential of the species getting oxidized and the reduction potential of the species getting reduced. Now standard hydrogen electrode, which is also written as SHE, is used as the reference electrode. So basically this is represented by the given cell representation. Here you have your H2, which is going to H plus. Or if you are taking it on the right side, that is on the reduction side, then your H plus will go to H2. All of the things are taken at the standard condition, 1 molar concentration, 1 atm pressure. Clear? So it of course it depends upon the way that you are putting it. If you're putting on the anode side, then we will write in this way. If you're on the cathode side, we will write it in the other way. Now the difference between the potential acquired for the evolution of gas and the standard potential of the gas is called the overall potential or overall voltage. So using this you can calculate what? You can calculate the standard potential of the given cell. If you put this on the anode side, then you will get the reduction potential of the given species. Clear? Now is the electrochemical series. So basically it is the tendency to lose the electron. Okay, it is a tendency to lose the electron. It is the series that is being calculated at 25 degrees Celsius. So this is the series. So what are we doing? Is we are gaining electron. We are going from Li plus to Li, K plus to K. And if you move from up to down, you can see that the value is increasing. So the reduction potential is increasing down the group. Okay, down this table. If your reduction potential is decreasing, that increasing, that means your reduction power will decrease, means the tendency to reduce other will decrease. Similarly, if you go from bottom to top, you will see that the oxidation potential will increase. Okay, it's very obvious because oxidation potential will be negative of each of this. So obviously it will increase from bottom to top, and the reduction power, sorry, the oxidizing power will decrease from bottom to top. Okay, clear? The same thing is mentioned here, the increasing tendency for reduction and the increasing strength of oxidizing agent, because on moving top to bottom the reduction potential is decreasing, so your strength for oxidizing character, sorry, increasing, so the strength for oxidizing agent will also increase. Clear? The same goes for this thing. Now moving to a very important part, which is the Nernst equation. So first of all, if you are trying to calculate the E cell at equilibrium, then it will be always 0. You don't have to worry about it. So keeping that in mind, we can write here E naught cell is equals to 0.0591 by n log k. So this is for equilibrium. Okay, where log k, where k is the equilibrium constant and 0.059 is being calculated at 25 degrees Celsius. Now how will find the Gibbs free energy? So it is given by delta G naught equal to minus n E naught Fe. So if it is not for standard condition, you will just drop off this naught. Okay, it's mentioned here also that this delta G naught is for standard Gibbs energy. Now, what will happen if in case you have to calculate your E cell and it is not equilibrium, then it is E cell is equals to E naught cell minus RT by NF log Q. Sorry, ln Q, right? RT by NF ln Q. Clear? So if you just put the values of RT by F, then you will get what? Then you will get your value as 0.0591 in case of 25 degrees Celsius. Okay, so this was for the theory session. Okay, students. Now we will move on to the question part. Disclaimer: the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owner of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the images. So what are we going to do today? So basically we'll practice questions some. We'll practice some questions. So basically it questions will be 8 questions will be there and we shall move through the concept that we have encountered today. So question number 9. So each question will give you 30 seconds to solve this question. So you can try and solve each of them. That would be very beneficial for you as well. So question number 9 says that a current of 2 ampere is passed for 5 hours through a molten tin salt to deposit 22.2 gram tin. What is the oxidation state of tin in salt? Okay, your options are A plus 2, B plus 5, C plus 3 and D plus 4. And atomic weight of Sn is also mentioned. So it is basically a question from Faraday's law. Very easy to solve. So you have 30 seconds to solve this question. Your time starts now. Okay, now let us see the solution, how we'll solve it. So this was our question, right? So for those who have solved it, the correct answer is A plus 2. So we know the formula W is equals to ZIT, right? So we have used that formula only. So instead of that, we have taken the equivalence of 10, which is equals to I multiplied by T by 96500. So what is the equivalent weight? So equivalence of 10 is 22.2 by equivalent weight. So this is our formula. So the mass of tin is already given 22.2 gram. So W is equals to ZIT. So W by Z is equals to IT. That thing is written here. Okay. So how is the equivalent weight calculated? So it is 59.5 in this case, and your valency will be atomic weight by equivalent weight, which will be 118.69 by 59.5. So we have first calculated the equivalent weight, and your valency is calculated by atomic weight by equivalent weight. So that will give you an approximately 2. So basically 2 will be your answer. So we can write the equation also in this way, that your Sn2 plus is taking 2 electrons and going to Sn. So therefore the oxidation state of tin is plus 2. Moving on to the next question. Question number 10. Question number 10 says that in electrolytic cell, flow of electron is from, options are A, cathode to anode in solution, B, cathode to anode through external supply, C, cathode to anode through internal supply, and D, anode to cathode through internal supply. You have 30 seconds to solve this question. Your time starts now. So it's a theoretical question. So let us see the solution. So we have to see that in an electrolytic cell, flow is electron is from where to where. So it is basically from anode to cathode. We have seen just now through the internal supply. So again, that same thing is written. So I think we don't need any much more explanation regarding this question. Moving on to the next question. Question number 11. Question number 11 says that when the sample of copper with the zinc impurity is to be purified by electrolysis, the appropriate electrodes are A. So there are columns of cathodes and anodes, right? So in A, cathode is pure zinc and anode is pure copper. B, cathode is impure zinc and anode is pure copper. C, cathode is impure zinc and anode is impure sample. D, cathode is pure copper and anode is impure sample. So you have 30 seconds to solve this question. Your time starts now. Okay, now let us see the solution. So basically it is asked that when the sample of copper with zinc impurity is to be purified, so what is the appropriate setup that we'll do? So very simple. On the cathode side we'll take the pure copper, and on the anode side we'll take the impure copper, right? And that will be helpful in what? In purification of this impure sample. Okay. So moving on to the next question, question number 12. Question number 12 says that your lambda naught for NH4OH is equals to, options are A, lambda naught of NH4OH plus lambda naught of NH4Cl minus lambda naught of HCl. Option B, lambda naught M of NH4Cl plus lambda naught M for NaOH minus lambda naught M for NaCl. Option C, lambda naught M for NH4Cl plus lambda naught M NaCl minus lambda naught M of NaOH, and last option, which is lambda naught M of NaOH plus lambda naught M of NaCl minus lambda naught M of NH4Cl. So you have 30 seconds to solve this question. Your time starts now. So this is a question from Kohlraa's law. How I will solve it? So basically we have to do the suitable calculation so that this adds up to NH4OH. So for that we have taken the case of this. Okay, so we have taken for NH4Cl, we can add NaOH, and that can be equals to NH4OH and NaCl. Now when we will rearrange this, we will get this thing. Now we will, if we will add this, then this Cl and Cl will get cancelled, and your Na and Na will get cancelled, because it will be the individual contribution from cation and anion, and the thing that will be left is your NH Miss lambda naught m of NH4 plus and lambda naught m of OH minus, and that is the thing we were looking for. So your correct answer is this, right? Okay, moving on to the last question for today. Question number 13. Question number 13 says that we have a cell which is represented half H2 plus AgCl gives us H plus aqueous plus Cl minus aqueous plus Ag solid occurs in the galvanic cell. Your options are A. So A is having Ag to AgCl in solid, KCl as aqueous, the double line for salt bridge, AgNO3, then AgS. We have again PtH2 HCl, AgNO3 and Ag. Then we have PtH2HCl and AgCl Ag, and last one is PtH2KCl and AgCl Ag. So you have 30 seconds to solve this question. Your time starts now. Okay, let us see how can solve it. It is a question of cell representation. So this was our cell reaction. So here H2 is going to undergoing oxidation to H plus, and Ag plus is going reduction to Ag solid, right? AgCl is going to Ag solid. So we can write it simply that our H2 is going to H plus and our AgCl is going to, that our Ag plus is going to Ag. So this was your correct answer, that is C. Okay, so this was all for today's question session. Thank you.